Okay, so let's take a look at a third problem. This one involves a commercial airliner, and it's going to speed up to get ahead of a storm. So it's going to increase its velocity from 200 meters per second to 245 meters per second. So that tells me what its initial and final velocities are. 200 meters per second, 245 meters per second. Okay? And it also tells me what the acceleration rate of the airliner is, and that is at about 1/4 of a meter per second squared. Okay? Might not seem like much, but when you're accelerating at a constant rate, that is, constant acceleration for a long period of time can build speed tremendously. So let's take a look and see what it wants us to figure out. In part A, it wants us to know how long did it take the airliner to reach the desired speed at that acceleration. How long? So that's time. It wants to know the time interval it took to speed up. And then what distance, or you could also say displacement. Well, one thing we're not doing here is we're not talking about direction. So sort of using those terms interchangeably, not totally correct, but we want to know how far it went. How far did it go over this time period that it was accelerating, and based on the units here, especially with that acceleration in meters per second squared, I'm probably going to end up with a displacement in meters. So that the problem then says, well, how far is that in miles? Because we live in America, and we tend to think about things in miles and not in meters or kilometers. Okay, so in part A, what we're going to do is we're going to figure out the time interval it took for this acceleration. I know initial velocity, final velocity, and acceleration. So in going through my kinematic equations, I'm starting to get good at this, more comfortable. I say, okay, it has to have t, and the only other variables are final, initial velocities, and acceleration. I can see that number one, or my first kinematic equation on this sheet, is going to be the way to go. I will have to do a little bit of mathematical manipulation to get it in a format that puts t all by itself. Then I go ahead and I plug in my knowns. 245 meters per second minus 200 meters per second over. Okay, so let's see here. This is good. I don't even need a calculator. 245 minus 200, I know that. That's 45. 0.25 meters per second is the same thing as 1/4 of a meter per second squared. So flip that up. So it's basically multiply 45 times 4, and that's 180 seconds. So I almost put the wrong unit in there. 180 seconds, or just use a calculator to figure that out. So that's my time value. I'll write it again. 180 seconds. Okay, in part B, I want to figure out how far did the airliner go in that amount of time, and again, I want to only use the things that I've been given. So I'm looking for an expression, a model that has displacement in it, has initial velocity, final velocity, acceleration. So can't use the first one, doesn't have displacement in it. Can't use the second one because it also includes that time variable, so that'd be two unknowns. Same thing with the third. I go down to my fourth kinematic equation. I'd say, okay, that's a known, that's a known, and that's a known, and there's displacement. So I'm going to choose that math model. Okay, and I'll do a little bit of rearranging, some algebra fun. Okay, and now I just have to go ahead and put in my numbers for the variables. So 245 meters per second squared minus 200 meters per second squared. This is an opportunity to where you can make a simple little math boo-boo. What I see a lot of people do sometimes is they will go ahead and say, 245 squared minus 200 squared, well, that's the same thing as 45 squared, and it's not. So we have to take those numbers and make sure we square them individually, so you get. And you also have to square the units. Okay, so I've simplified a little bit of the math here. Put the rest of this into my calculator. I'll go ahead and get a numerical answer. Let me just make sure that my units make sense. So here I've got meter squared over second squared minus meter squared over second squared. That's just going to remain meter squared over second squared, but then I'm going to divide by meters per second squared. So what's going to happen is this second squared, they'll take each other out. This meters will take out one of those meters, and I'm going to be left with an answer in meters, which is what I would expect. Calculator is going to tell me that my displacement is about 40,000 meters, which there are 1,000 meters in a kilometer, so that we could also rewrite that as 40 kilometers. If you like doing it the long form, you do it like this: 1 kilometer is 1,000 meters. Cross that out, divide by 1,000, and that's how you get 40 kilometers. But the answer asks for it in miles, and the next unit conversion that I would do is I would have to know that in 1 mile there's 1.61 kilometers. 1.61, and I'll take that out, and when I divide 40 by 1.61, I get about 25. So that would be my answer. It took about 25 miles for that plane to go ahead and accelerate and speed up to outrun the storm. So there's another pretty quick example of doing simple kinematic equations in physics. I hope this helps you out.